Okay, so I want to very quickly go over the law of definite proportions and the law of multiple proportions. So you know how to do those for the Alex homework this week. I'd rather make a little video here and then let you work through some problems than move the problem, to be honest. And I think seeing it twice help you understand it better next week when we cover it in class, because I'll go over this again in class. But for the Alex homework this week, what is the law of definite proportions? Okay, so just break down like exactly what this term means, right? Definite, meaning that they are set. They are concrete proportions, and proportion meaning that the ratio or the number of one type of atom to another type of atom, specifically when we're talking about this particular law, we're saying that there is a set ratio or a set proportion for any type of compound of the oxygen atoms to hydrogen atoms, for example, here, when Joseph Proust did this analysis of water, or for any type of compound. So every sugar molecule is going to have the same number of oxygen atoms, carbon atoms, and hydrogen atoms. Now, the law of definite proportions is from a time before we could actually see how many of each type of atom there was. Instead, you could have water and you could do a decomposition reaction. So if you took 18 grams of water, you do this decomposition reaction, it's usually electrolysis. It splits all of the water atoms into hydrogen and oxygen separately, and then you can weigh the masses of those. So 18 grams of water results in 16 grams of oxygen, 2 grams of hydrogen. That's the case for any sample of water. So then we can get a mass ratio, and this is the proportion part. That's 8 to 1. That's 8 grams of oxygen to 1 gram of hydrogen. Okay, so the mass ratio in ammonia, nitrogen to hydrogen in ammonia, is 4.7 to 1. So these are, I can highlight this to help a little bit. Nitrogen is the 4.7, and the hydrogen is the 1. So if a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? So this kind of comes down to recognizing conversion factors, but this ratio is a conversion factor because it's telling us that we have 4.7 grams of nitrogen equals or or however you want to say it, 1 gram of hydrogen, because I could have just written the H there. We'll do that to be consistent. So if I'm starting with 10.0 grams of hydrogen, I can convert that into grams of nitrogen using this definite proportion or this ratio of masses for nitrogen and hydrogen. So go ahead and pause, figure out how you plug this in. Okay. So hopefully you remember that this is a conversion factor, so we want to cancel out units. These are the units that I have, grams of hydrogen. So 1 gram of hydrogen goes on the bottom, 4.7 grams of nitrogen goes on top. So this should be something like 47 grams of nitrogen, and our answer here then would be D. All right, I'm going to skip these specific examples. You'll get lots of examples when you're doing this in Alex. I want to talk about the law of multiple proportions. So the law of multiple proportions is slightly different from the law of definite proportions in terms of what we're talking about. So law of multiple proportions is talking about different compounds made from the same types of atoms. For example, earlier of water, water is H2O, so it's made up of hydrogen and oxygen. However, that's not the only compound that can be made of hydrogen and oxygen atoms. In this case, there aren't that many that exist in nature, um, but we could change that ratio. So what if we had, instead of 2 hydrogen atoms and 1 oxygen atom, right, we could have 1 hydrogen and 1 oxygen, or we could have 2 hydrogens, and 2 oxygens. So again, this is a sort of law that comes from the time before we were able to count atoms in these things, and it was another way to confirm and lead to the idea that in the future, with more sophisticated technology, we might be able to prove this more precisely. What is the multiple proportion then? Really what the multiple proportions here is, in the law of multiple proportions, is saying that for each of these compounds, if I set one of these elements' masses to be 1, so if we said oxygen's 1, the mass of the hydrogen in each of those would be a proportion, or would be proportions of each other, and specifically integer proportions. And this, I think, maybe you have to think through it a little bit more, but if you just look at H2O and HO, how is the mass of hydrogen in H2O different from the mass of hydrogen in HO? H2O should have 2x the mass of hydrogen when compared to hydroxide, which is this, with 1 hydrogen. The mass of the oxygen is still going to be the same, though. So this is the law of multiple proportions, which hints at or suggests that atoms are always combining in whole number ratios, similar to what we saw with the law of definite proportions. So another example of this would be carbon monoxide and carbon dioxide. So carbon dioxide has 2 oxygens. Carbon monoxide only has 1 oxygen. So if we make a ratio like the definite proportions that we saw up here, right, so law of definite proportions is the mass of oxygen to the mass of hydrogen. It's done that way so that you get a whole number. We're really saying that the definite proportion of carbon dioxide is 2.6 grams, I'll write the oxygen in here, of oxygen for every 1 gram of carbon. And we compare that to the definite proportion. So let me write this. This is the definite proportion. We're comparing it to the definite proportion. Again, that's for 1.33 grams of oxygen. If we compare these definite proportions of compounds that are made of both carbon and oxygen only, then the ratio of oxygen is going to be equal to 2. Because we set the other one to be carbon, which is just 1 gram. So if I take that ratio, which is 2.67, and that's 2.67 grams of oxygen for every 1 gram of carbon. And then down here, this is the mass of oxygen that combines with 1 gram of carbon. Also, it's 1.33 grams of oxygen for 1 gram of carbon. We're leaving off the 1 gram of carbon because it's 1, right? It doesn't affect this calculation. So that gives us a ratio of 2. And that will be the case for anything, any compounds that are made of the same types of atoms, but different numbers of those types of atoms. Law of multiple proportions, different compounds. All right, I think it helps to see more examples of this, so we'll do this one here. Hydrogen and oxygen both form water and hydrogen peroxide. We saw that before. Do this decomposition reaction of a sample of water, we get 0.125 grams of hydrogen for every 1 gram of oxygen. And then we do a decomposition of hydrogen peroxide, so different compound. We get 0.0625 grams of hydrogen for every 1 gram of oxygen. So, give you a second here to pause if you want to just try this whole problem. Okay, so I'll explain the first step of this, and then I'll give you another opportunity to pause. The first thing that we want to do is, for water and for hydrogen peroxide, we want to determine sort of their law of definite proportions proportion. So for water, and this is pretty easy because we were given already that this is 0.125 grams for every 1 gram. For water, our law of definite proportions would say that 0.125 grams of hydrogen for every 1.00 grams of oxygen. And for hydrogen peroxide, we would get 0.0625 grams of hydrogen for every 1.00 grams of oxygen. And I just pulled those numbers right out of the problem, right? How do we use these now to show that the proportion, the law of multiple proportions, I should say, applies to water and hydrogen peroxide? And I'll give you another opportunity to pause. Okay. So remember, the law of multiple proportions says that there's basically a whole number integer proportion between compounds made of the same type of atoms, but different numbers of those types of atoms. So water and hydrogen peroxide, we would take this ratio, and I can simplify this ratio because we really only need the part that's not 1, which is the 0.125. So for water, 0.125 divided by 0.0625, right, that one there, this one here. And so if you do that, this should equal 2 exactly. You might have done this the other way around with the 0.0625 on top, 0.125 on the bottom, and then you would get exactly half. And that's a sign that you've just got your number inverted there. You generally want the larger number on top, smaller number on bottom. Okay, so hopefully that helps when you go into those problems for the law of multiple proportions. Just remember it's comparing two separate compounds, and we need to get the definite proportions for those individual compounds and then compare those definite proportions of the different compounds to each other to figure out if there is a ratio like we saw here with hydrogen peroxide and water. If it doesn't come out to a whole number or a whole exact fraction, then it does not follow the law of multiple proportions. I do really think Alex is going to help you out a lot here just by going through practice problems and reading the explanations.